So you don't have to follow what's in the homework exactly. It's just, it is hopefully helpful if you want to show something that's similar to what's in the homework. But you don't have to do those steps if it isn't relevant for what you're doing. It's just meant to be giving you some tools and some things to think about. Yeah. No, it's not very... The idea here is that it's not supposed to be very directed. It's supposed to be your ideas as to what you think are the important pieces to talk about. So the only thing that I really want you to do is I definitely want you to calculate the Ekman transport and possibly also the Ekman upwelling, depending on where you are, from the wind stress, and then compare it to something in the model. But those pieces, exactly how it fits together and which way you do it and which kind of graph you make that makes it most meaningful, you should play around with it some to make the most sense to you. Okay? Yeah, I mean, it's not a... Yeah. Oh, they closed that one too. It really is dark in here now. Okay. So last time we talked about the geostrophic flow that comes from pressure anomalies. And we talked about that in the eastern boundary currents, so like the upwelling driven currents. And then we started talking about it in the gyre as well. And remember, we specifically focused in the constant density case that really all of the pressure anomalies are coming from the sea surface height anomalies. And so then you could start thinking about that, and the sea surface height over the Coriolis parameter was actually acting as a stream function for the flow. So remember, as we went from one side of the gyre to the middle for an anticyclonic, high pressure, subtropical gyre, the sea surface height would go up and up and up. It would reach a peak at the middle, which was between the equatorward flow and the poleward flow, and then it would drop back down. And if there was just loop-de-loop going around and around in circles, the sea surface height would be the same on both sides of the basin with a high in the middle. That was the way that the high pressure was. And we talked a little bit about the fact that the bigger currents were on the western side of all those gyres. We don't have a reason for that yet, but it's something we want to get to explaining. So today we're going to do a little bit more about that. We're going to think about it from the perspective of vorticity, which is also a new concept. But we'll talk about vorticity some, we'll talk about potential vorticity some, and then we'll start to see how that fits into this concept of the gyre. And one of the reasons why the vorticity is helpful is because we talked about that amplification of the system. So just less than 10 Sverdrups of Ekman transport was driving like 100 Sverdrups of geostrophic transport. So there's this big amplifier effect. So we wanted to, vorticity is a useful way to think about exactly how the amplifier works, like how that system fits together, why you get such a big response to such a relatively small amount of wind forcing. So we'll go on how that goes. And again, as usual, we will do our review of balances at the beginning to start so that you guys, clearly, this is important. And then let's talk about vorticity and potential vorticity, which the editor of Nature this morning was tweeting about what potential vorticity was. So I sent in a tweet about potential vorticity and defined it and was very happy that I could because I was thinking about today's class. And then I said, well, of course, Abby's going to tell us why potential vorticity doesn't work next week. So this is a topic that's on the whatever, it's timely. Okay, so here's the momentum equation again. We've seen this a bunch of times. We have advection on that side, Coriolis, pressure gradient, gravity, friction. Okay, so inertial oscillations. Advective Rossby number is small, temporal Rossby number is order 1. And it wobbles. It's the wobbles we saw in the tank. And the wobbles are how often do they occur? Twice per rotation period, so twice per pendulum day on the Earth. So at the pole, it's twice per day. As you get to the equator, the pendulum days are getting longer and longer as the Coriolis parameter is going down. The Ekman layer is a balance between the Coriolis parameter and friction. The hydrostatic balance is the only vertical balance we've been talking about, and it's between gravity and the vertical pressure gradient. Geostrophic balance is pressure gradient in the horizontal and the Coriolis force. Oh, they're cupcakes, which are also circulating.
From another event.
That's good. Anybody else want a cupcake?
They're swirly like vorticity.
Oh yeah, they've got vorticity. No, they're also timely and topical. Yeah. No. And then the Taylor-Proudman theorem, remember, is a combination of the geostrophic part, the hydrostatic part, and it gives you columnar motion under what additional assumption? Staring at all the words that have all of the secrets in them. But which one is the one that's the key other one? So we get this one, and this one, and this one. Just tell us which terms to neglect. So that's not it. And this one is sort of a geometric feature, which we talked about. But what about this? It's the baroclinicity is 0. So what kind of fluid doesn't have baroclinicity? Or two kinds we've talked about, actually. What does baroclinicity mean? Density and pressure are not aligned, right? So there are interesting pressure, density variations along a pressure surface, or interesting pressure variations along a density surface. It doesn't matter which way you think about it. Because the ocean is nearly constant in density, it's probably easier to think of the pressure surfaces as being really close to horizontal, with the one exception of the sea surface height tilt. But if there's warm and cold on that same pressure level, or buoyant and less buoyant, buoyant and dense, or fresh and salty, then that would lead to baroclinicity. That is baroclinicity, the fact that they are not aligned. So what do we call it when they are aligned? Barotropic, which means that the pressure is just a function of the density, or the density is just a function of the pressure. Pressure is pressure as a function of the density, or you could invert that and say the density is just the density as a function of the pressure. Okay? So Carl Wunsch has in the appendix 6 other ways that the word barotropic is used casually among oceanographers. This is the right one. This is the true, that's the definition. But then barotropic also gets used to express things that don't vary with depth. Why is that relevant?
Because pressure and depth are usually related.
Because pressure and depth are usually related, and because there's the Taylor-Proudman theorem, which says that things don't vary with depth. They move in columns in a barotropic fluid. So sometimes people will say the velocity is barotropic, which means it doesn't vary with depth. And what they're thinking of is this theorem, but they're not really doing all the steps. They're jumping to the end. Okay? And then another thing that people sometimes say is they say, well, the barotropic flow, and they mean the flow at the surface. Or they mean the flow at the bottom. If it doesn't change with depth, that's not crazy. But neither of those is the barotropic flow. When there's baroclinicity in the fluid as well, it's kind of tangled up together. You can separate into a baroclinic part of the flow and a barotropic part, but it takes more care than just the top or the bottom. Okay? So, this is what? It could also be taken as the mean. So all 3 of those are reasonable definitions because the baroclinic velocity is not reasonably defined. So you have to kind of decide what you want to do. What we were talking about the other day, last time, where we said, well, surface height variations drive a geostrophic flow at the near surface. You could take that to be the barotropic flow, but really it's the surface geostrophic flow. That's where it is. And then if the pycnocline is bowing down and making some baroclinicity, going down or up, then that surface flow won't be the same as the flow below the pycnocline. So that's the pillows and bricks conversation we keep having, is to try and make baroclinicity seem intuitive, but it's not very. And then at the very end, last time we talked about the shallow water equations, which is an equation set that looks an awful lot like one layer dynamics, except it handles both a surface and a pycnocline bowing away in a kind of simple way. It makes them look similar with just a reduced gravity, G prime, which is gravity times the relative change in density from the upper layer to the lower layer. Okay? So there are a lot of these pieces coming together. We're going to hit back on reduced gravity in a little bit. We're going to hit back on layered models in a little bit when we talk about potential vorticity. And that's kind of a helpful thing to think about. We'll keep coming back to that. But this is always kind of lurking. And then thermal wind is our deviation away from Taylor-Proudman theorem. We have two ways, we've actually discussed two ways of making vertical variations in the velocity. One of them is thermal wind, and that's because you have a buoyancy gradient, light stuff next to dense stuff, warm stuff next to cold stuff, fresh stuff next to salty stuff on the same pressure surface. So if they're side by side, then it's got to be baroclinic, because if it was barotropic, every pressure surface would have the same density, the same buoyancy all along them. Okay? So, and that leads to a shear, dv dz, velocity changing with depth because of this. What's the other example where we had a dv dz? Maybe I can go back to this. You can kind of undo these assumptions. No hurry. And it's relevant to this paper, and it's relevant to the way you would diagnose the effects in this paper. Yeah?
There's a geostrophic flow like beneath the Ekman.
Right. So Ekman, if the Ekman number was not small, we could have gotten a d by dz by bringing back in the friction term. Remember the Ekman spiral that has a dv dz. So in getting to this Taylor-Proudman, we have to keep the baroclinicity low, and we have to forget all those interesting frictional effects. Okay? So those are pieces to keep in mind as we're going along. All right. Here's the Gulf Stream. I don't know why I had that in there. Just to show that, I guess just to show that it's baroclinic. So we looked at this last time. These are different profiles of the velocity field in the different locations along the Gulf Stream. And you can see that it is not constant velocity top to bottom. It actually goes slower at the bottom, or in some locations even reverses its direction below. So it is baroclinic. So what does that mean about the temperature difference across the Gulf Stream, or the buoyancy difference? It's non-zero, yeah. And it's actually warmer on the east side, but it doesn't have to be. That's just part of that's thinking through how the thermal wind works. Thermal wind is involved in this. How do I know that this is thermal wind and not Ekman? Seems to be rotating.
Actually, you can't tell.
Yeah, so how can I tell by looking at the numbers on this figure? I'll make it a little bit more precise. This is too deep of a shear for Ekman. This is below the Ekman layer. So the Ekman layer might be in the top 100 or 200 meters at most. We're looking at shear that's down at 1,000 meters. So it has to be something. So there's not much friction down there because the Ekman number, remember, the Ekman number, this guy, has a depth scale in it. And we said that when you crunch through the numbers and plug in for what we think good eddy viscosity is for the ocean, this is order 10 to 100 meters. It's not 1,000 meters. The ocean's not that viscous. There's not that much mixing by turbulence in the ocean. Okay? All right. Slowly we get all these pieces together. All right, cool. Okay, so our stacks of pillows and bricks. Last time we talked about pillows and bricks, and so this is a what? A barotropic or baroclinic flow? I know, in some way. Jumping back and forth between definitions and application of those same definitions to different problems.
It's barotropic, right?
It's kind of like, sometimes it's called equivalent barotropic, which it's like barotropic in the upper layer, but then there is, because the pycnocline gets pushed down, there is actually a density gradient, a buoyancy gradient down there, but frequently we just would assume that it cancels out the motion below. So it is a baroclinic flow. It's baroclinic because the pycnocline is depressed, but really the only interesting motion is because of this sea surface height anomaly. And what the pycnocline does is it just cancels it out. So we can use our reduced gravity system. We could set the second layer velocities to 0, which then gives us a constraint between the upward elevation and the elevation of the pycnocline, and that's the one that gets us back to that reduced gravity that looks just like a one-layer system forced by the surface, but it's not. It's a two-layer system with the bottom layer not moving. Okay? All right, so that's our review. Okay, so something new. So how many of you have heard of vorticity before? A little. Okay, so the vorticity is the curl of the velocity. Okay, so what is a flow that has a lot? So if we think about the flow, the Bart Simpson flow going down the toilet, does that have vorticity in it or not? Yes, because it's spinning, right? It's also converging, so it probably has some, horizontal convergence and some vorticity because it's spinning. Okay? So the curl, remember, if you want to calculate the curl of a vector field, the way it works, the curl of a vector field is you wrap your fingers around. If it's curling around, and the direction that your thumb is pointing will be the direction of the curl. And it doesn't matter what direction it's in. This is a fully three-dimensional object. So it could depend on the vertical velocity, the horizontal velocity, the other horizontal velocity, the vertical velocity, with lots of derivatives and complicated directions. Okay. In the ocean, we are primarily interested in the vertical vorticity. Why would that be? So that's the one that goes around like this. Exactly. So the horizontal velocities are the big ones. And so the vertical vorticity is the one that talks about the swirling of the horizontal velocities. So that's important. It actually turns out that the overturning circulation, which we talked a little about in the beginning and we'll talk about again, actually has a bigger vorticity than the vertical vorticity, which I did not know and no one had ever told me until I calculated it like last year just as a lark. And then it took me about 4 different times to convince myself that was actually right. But we'll talk about that later. But the traditional understanding of the horizontal motions, like the gyres and the ACC, have everything to do with the vertical vorticity. And if you wanted to do this on a sphere, you could take the curl on a sphere, which has a lot of nasty factors. But on our happy little tangent plane approximation, we can just use x's and y's, with y being the north-south direction, z being the vertical, and x being the east-west. Same way as we have been all along. Okay. So vorticity and the circulation. So this is the circulation. It's the velocity dotted into an integral of length as I go around a closed loop. So the circulation would be, if I went around in a closed loop, it would be the integral of my displacement dotted into the velocity in the direction I was moving as I went around the loop. Okay? So Stokes Theorem, like the divergence theorem, is a little bit of vector calculus, because this is the curl of the velocity, it equals this funny integrate around a loop circulation. So the vorticity, this is the picture we're going to think of it. Here's a so-called vortex tube, which is, if we had a lot of time to talk about fluid dynamics, we would talk all about the fact that vortex lines in fluid flow don't terminate. They just wrap around and around. And so all fluids are just kind of chock full of these vortex lines that are connecting one part of the flow to another. If you take a plane and slice through one of those vortex tubes, the circulation, that is the velocity along this direction around that loop, is just the area integral of the vorticity punching through that surface with a normal direction. So it's the projection of the vorticity vector onto that. So if I put more vorticity in here, what happens to the circulation? Goes up. If I take a bigger area, what happens? It increases if the vorticity is constant. But interestingly, if this is the only vorticity, and suppose the vorticity was 0 outside, I could take any area I want, and the circulation would still be the same. So it's the amount of vorticity inside that area that controls the circulation. Okay? And this isn't like a force balance or anything. This is just calculus. It's the definition of vorticity being the curl that gives you this relationship to the circulation. So there are two different ways to think of the vorticity. You can think of the vorticity in the gyre, so you can say, at every point's got vorticity, and I need to understand where it's coming from. Or you can say, I take the integral of the vorticity over the area of the gyre, and then I know the circulation of that gyre. The flow going around and around times the length of the flow. Okay? So two different ways to think about vorticity. Okay. We're on a rotating planet. So if you have seen vorticity in an engineering class, frequently what they say is, from now on, all of the flows we're thinking about have no vorticity in them. And so vorticity is 0. And then they go on to prove lots of other things. We're on a rotating planet. So what do you think that means about the vorticity? If vorticity is the spinning of things, we're kind of always spinning when we're on a rotating planet. So let's take the simplest case, which is, what if we're just in solid body rotation? So what if the fluid is just rotating like along with the Earth, around and around in a circle, but it's not moving relative to the Earth? Okay? Then the absolute velocity, we saw this when we derived the Coriolis force and the centrifugal force, is just the rate of angular rotation crossed into the vector of angular rotation crossed into the distance from the rotation axis. So this tells you how fast we're going around. And remember, this is the one, what would this be in the frame of the Earth? What's the velocity due to solid body rotation in the frame of the Earth?
Did you say in the frame of the Earth?
Yeah, in the frame of the Earth. 0. It's not moving. So this is what it is if you're standing off and watching the Earth spin in an inertial frame. This is the velocity. So if I take the curl of this, I actually get a vorticity. So there is vorticity associated with the solid body rotation of the planet, and it's 2 omega. So it's not the angular frequency, it's not the angular rotation axis, it's twice that. And in the vertical direction, it's 2 omega dotted into the vertical, whichever direction I am, whatever latitude I'm at, which is just F. So, if you're into coincidences, you might think that this was a thing. This is not a coincidence. The reason why F is the thing we care about is because F is the measure of the vertical vorticity having to do with the rotation of the planet. The reason why 2 omega is the 2 that's drifting around is largely to do with the fact that the vorticity associated with the rotation of the planet has a 2 in it. So when we think about the fluid dynamics that's relevant, that 2 keeps popping up. And when we think about the dot product of 2 omega and the vertical, the F bit, the vertical component of local planetary vorticity, you might call it, that's the thing that goes into our Rossby number and everything else. Okay? And in fact, so, you guys, do you know what a Foucault pendulum is? A pendulum that's a really big one that, like, you can actually see the motion of the planet as it rotates around. It's an inertial oscillation, essentially superimposed on a pendular motion. So, in Foucault's paper, he doesn't know why there's a function of the cosine of latitude. And he says, I can't be bothered to mention that here in this short paper where I described this pendulum. But I've done this experiment at different latitudes, and I've determined that there is a cosine of latitude factor. But this is a pretty subtle thing, and it's really because this is a vector-like object, the angular rotation, and then you dot it into the vertical to get the relevant vertical component of vorticity is part of that answer. Okay, so the Coriolis parameter is equal to the vertical component of the vorticity from the Earth's solid body rotation. Okay, let's add some relative motion on top of that and see what we get. So now we have the absolute velocity is the solid body bit plus motion relative to the Earth. If I take the curl of that, I get my 2 omega from this term, and then I just get the curl of the relative velocity, which we can call the relative vorticity. Okay, absolute vorticity, planetary vorticity, relative vorticity. And if I take the dot product of this guy into the vertical, local vertical direction, wherever I'm at, I get F because of this one, and then I get some other thing, which is the relative vorticity, the vertical component of the relative vorticity. So that's the sense of spin in the horizontal that has a vertical axis pointing upward. And we can wonder about which one of these is bigger. We can take their ratio, put zeta over F. Well, zeta is a velocity per unit length. That's what it is, right? It's the curl, so it's a derivative of velocity. And F is just F. That's the Rossby number. So another way of thinking about the Rossby number is whether the dominant vorticity is from the relative motion or the dominant vorticity is from the planetary motion. So when we say small Rossby number, we could say, well, the velocity compared to F times L, which is sort of an abstract object, is a small thing. Or more meaningfully, we could say that the relative vorticity, the vorticity in motion relative to the planet, is small compared to the vorticity of the planet itself. Does that make sense to everybody? So that says the same thing. Okay. So we have the vorticity now. We have some sense of what it talks about. There's the vorticity. It links to the circulation. We have this integral formulation. And we know that it's just the curl of the velocity. So what's the equation governing how the vorticity evolves? We have a momentum equation, but we don't yet have an equation that's like that for the vorticity. Okay? And it turns out that it's, you basically just take the curl of the momentum equation and then work out all of the nasty vector calculus to get that to work. So you do a lot of vector calculus bits and pieces, and now, so that's the momentum equation. You do this, you get this, and then you do this guy, and then you have to work out that, oh, look, you've got this complicated part. There's a density here, and there's a pressure there, and it comes out to some fancy thing like this. And so then you use this one, then you use this one. So you're kind of chugging along. I don't want to spend much time other than to say that it is a relatively straightforward but tedious explanation to get from there to there. But what you end up with at the end is an equation that instead of the rate of change of velocity, you have the rate of change of vorticity. And then you have an advection term. So these two together are just the material derivative of vorticity. So vorticity, like momentum, like salinity, like temperature, has a big contribution that's just being carried around by the fluid. So if something is spinning over here in the fluid, and the fluid is moving that way, it just goes along with the fluid and keeps on spinning. At least according when these terms are unbalanced by anything over there. Does that make sense? Okay, now we get into the nasty bits. Here's one that is nasty, but that we never have to worry about really, because we're nearly incompressible. But if the flow converges or diverges, there's a source of vorticity or sink of vorticity because of that. This one, we don't have to worry about, because we normally are not converging and diverging. This is an interesting one called the stretching and tilting term. And sometimes people talk about this as this is the ice skater term. So does everybody know that when you ever see an ice skater spin, and then they like stick out their leg, and then they slow down, or they start spinning and they're like in a ball, and they stand up and they spin really, really fast, and then they get back down, or like whatever. It's a conservation of angular momentum, right? But a spinning hunk of fluid does the same thing. So if you stretch, that is, if your velocity is diverging in the direction of the vorticity, you will affect the magnitude of the vorticity. And it's in the sense that taller things are going to be spun up, go faster in whatever direction they were spinning to begin with, and when you compress them, they're going to slow down in whatever direction they were spinning to begin with. This is a little bit more complicated in the ice skater case because we could be interestingly diverging in like multiple directions at the same time and spinning in multiple directions at the same time. And so you would have to crunch all of the consequences to figure out what the total consequence was, but that's part of it. Okay? There's one other feature which is captured in that term. If our flow is sheared, so it's tilting over, you take, so if ddz of v is that way, then it would affect the vertical vorticity, and it actually also affects the horizontal vorticity. So if something's spinning like this and the flow wants to tip it over like this, now it's still spinning, but it's spinning in a different direction. So I've taken vertical component of vorticity and converted it into a horizontal component of vorticity by tipping it over. So this term takes care of that business too. So there's a stretching and tilting term which goes, if it's spinning like this and you stretch it, it spins faster. If it's spinning like this and you squash it, it spins slower. If you tilt it over, it converts some components of vorticity into other components of vorticity. Okay, so that's all. It's a little unwieldy, but they're sort of sensible. Then there's this one, the Barotropic torque. So let's look at what that key term is. Think about it for a second. Now, what's a barotropic fluid? It's a fluid where what and what are not aligned?
Density and pressure.
Density and pressure. So suppose these are the density surfaces, and these are the pressure surfaces. Okay, which way does the gradient of pressure point? And this is Z, so Z. Gravity's in that direction. So where is the big pressure? Down. And if these are isolines of pressure, which way is the gradient point? Perpendicular to the isolines, right? Because this is the direction in which pressure is increasing. Okay? Which way is the gradient of density point? Everybody's kind of playing in different ways. This way. Right? Because how do we know that the big density is at the bottom? Gravity. We don't really, but it tends to be. It could be at the top, but then the water would turn over. And in fact, this term is the term that talks about the tendency of the water to turn over. So let's see how that works. So gradient of density crossed into gradient of pressure. Okay, here's the gradient of density. Here's the gradient of pressure. What direction is the cross product of the gradient of density into the gradient of pressure? In, right? Start with your fingers this way, gradient of pressure, move them towards the gradient of, gradient of density, move them towards the gradient of pressure, where your thumb points is the direction. So the baroclinic term is in. So that setup with the gradient of pressure, gradient of density like that is trying to do what to the vorticity? It's in, so it's making vorticity in the in direction. So what does that do to the fluid? Yeah, answer got it. It's if the vorticity is being created in this direction, it's going to start tilting the fluid over. It's going to try and align the density and the pressure surfaces. So if they're not in alignment, if there is baroclinicity, this term says there is a tendency for the fluid to try and realign them. Okay? Does that make sense to everybody? Yeah.
What's the 1 over rho squared?
Oh, 1 over rho squared is basically just to get the units right. Or to put it a different way, you can go back to here. This is the curl of this term. So it was minus 1 over rho. So if you take the derivative of that, you get derivative of rho upstairs minus rho squared downstairs. So that's the minus rho squared. That's the derivative part. So it's coming from this term. Oh, what happened to the curl of pressure? If this is the curl of the coefficient, what happens to the curl of the gradient of pressure? You guys didn't take my intro to my Geo 350 class on math, because like almost every day I say, what is the curl of a gradient? And everyone looks at me. And then and eventually they start realizing that most of the time when I'm asking them something, it's like 0 every time. So the curl of a gradient is always 0. So the curl of the pressure gradient, doesn't do anything to the vorticity. But the curl of this coefficient gives you the baroclinicity term. Okay? And then there's a curl of friction, which means that you could try and spin the thing by frictional work. Like the wind on the top is trying to spin it that way, right? So there's certainly a possibility for that. Okay. So we didn't have the Coriolis force in this equation. So this was really a non-rotating momentum equation we were starting with and going. We could do the same business in the rotating equation. Now we have a Coriolis force. There's all this stuff. It's actually not that hard. You get the same equation, except plug in the absolute vorticity everywhere you see a vorticity, and the relative velocity everywhere you see a velocity. So the Coriolis term doesn't appear separately from the additional bit of planetary vorticity you got. So this is why I was saying that this is really the nice way to understand why F is what F is. F is the thing that is the extra bit of vorticity. But the vorticity equation is unchanged when you go in and out of rotating coordinate systems. The only game that you have to worry about changing is which vorticity it is you're talking about. Is it the relative vorticity or the total vorticity? It's usually the total. Okay? But to do it calculus-wise is kind of a mess. Okay, so we have this new object. Oh, one more. We could have also done it in the Boussinesq fluid. So the incompressible fluid with the buoyancy bit. And the only real difference is that I don't get the diverging term, still get the stretching and tilting term, and it's pretty much the same. And instead of this, the baroclinicity looking like this, the baroclinicity is a little simpler because it's just the curl of the buoyancy in the z direction, and the friction's the same. So it's a little simpler in the Boussinesq approximation fluid, but the full compressible fluid is, both of them are manageable. Okay, so let's look at a couple of examples of tilting and stretching, just to think about what happens. Okay, so this is the tilting and stretching term, or tilting and twisting. So here's our little vortex tube. What if I stretch it a little bit in the middle? Squish it. What would you expect to have happen? It's going to get advected with the fluid. That part we know. But then there's this. That's this term. But this one is doing something a little different. So when this is getting bent that way, it starts creating a little vorticity in that direction. So this vortex that's spinning along like this is now spinning a little bit in the upward direction. This vortex that's spinning along like this is now spinning a little bit in the downward direction. So one way to think about this term is just like that. And it's the same kind of thing as I was saying when you tilt over, you get new components of vorticity in the direction you're tilting into, which you might not have had before. And then this is the other one. This is the ice skater one. This is the stretching and squashing. So if you get stretched, you start spinning faster in the direction that you got stretched in. If you get squashed, you start spinning slower in the direction you got squashed in. Okay, now here's the exciting part about the rotating planet version of this. So remember I said the vorticity equation is unchanged in the rotating system, you just have to add on the planetary vorticity. So suppose we have a quiescent ocean that has no relative motion from the Earth, and then we stretch it. What happens? Did it have vorticity to begin with? Yes, it did from the planet. So if it was truly non-rotating fluid and we stretch it, then this would have been zero. This whole term would have been zero. Nothing would have happened. But in the planetary sense, when you're on a rotating planet, even if you're not moving relative to the planet, stretching still makes you spin. You start spinning in the same direction as the planet, only faster. So if I take a hunk of rotating fluid and pull it, diverge it and make it squish in, it's going to start rotating. What direction is it going to rotate? If it's rotating more in the direction of the vertical component of the planet. I always have to draw a picture. Let's draw a picture and we'll think it through. Okay. I take my little, here's my planet. The planet is rotating. Which way does it rotate? Right. The sun rises in the east. So it's going into the sun direction. That's the way. Toward the east. It's chasing its eastern side. Okay. So if I'm down here and I take a little hunk of water and I stretch it. So it converges in and it goes taller. Just like that. Which way does it start spinning? It was spinning with a component of this guy, so it was spinning like this. So we could draw the component. Here's the original vorticity. There's the component in the vertical. So it is spinning in that direction. So it'll spin even faster in that direction. So it'll spin like the pole spins. And is that a cyclone or an anticyclone? A cyclone. So it will spin in the same direction as the planet spins. So in fact, that is one way to think of how a storm works. You get a big convective event that uplifts in the middle, there's a big stretching term and the thing starts spinning. And it spins in the same direction as the planet. And the fact that it's not resupplied by air coming in means that you have a low pressure. You pull that air out and you push it out to the sides, but you don't bring it back in as fast. You end up with a low pressure system. So it's a low pressure when it gets into geostrophic balance and it starts spinning because of the vortex stretching term. What about down here? Do it here, what happens? Here's my vertical. Here's my component of the axis of rotation. So my vertical component is actually into the planet. So the vorticity is directed this way, it would start spinning that way. Which way is that way? The other direction. It spins like the South Pole is spinning. So this pole is spinning this way, this pole is spinning way, but this way is upside down, right? So you've got to flip over, and then it's spinning the other way when you're standing on your head because you're in the southern hemisphere, right? Is it cyclonic or anticyclonic? Still cyclonic. Right, cyclonic is it's counterclockwise here, it is clockwise here. It is still cyclonic in both hemispheres when you do a stretching term. If you squash it, it will be anticyclonic. Anticyclonic, anticyclonic, same way through. Clockwise, counterclockwise, flipped around the other way. Okay? And this happens even if there is no relative vorticity. That's the amazing thing. Like, even if the water looked like it was motionless, it still has the vorticity it inherited from the planet. So when you flush the toilet, it has inherited that vorticity from the rotation of the planet. And if you did that experiment carefully, you would actually see that it would be a cyclonic. It would stretch as it went down. So here's the, the pipe, the plumbing, and there's the water left up in the tank. You're stretching it in the vertical. It would start spinning cyclonically. Okay? If you did it right. Okay. So here's a beautiful movie to show you. Those are two vortex rings. And you can see that there are very beautiful interactions of vorticity. And the vortex rings are actually traps. So smoke rings, or these kind of bubble rings that, this is blown with a gun, I think, but dolphins blow these too. They do it for fun. It's a, this tells you that the vortex tubes are tracking the fluid, right? They're tracking, that bubble is tracking with the sense of rotation. And this one goes zoop through because there's a field of circulation around that vortex tube and around this vortex tube. So as it gets close, it starts sensing that little bit of the circulation and it accelerates it by. So I think the side that it is closer on is the one that accelerates. The one that it's farther on is the one that it doesn't go through so fast. That's because the vorticity is concentrated in the tube, and then the circulation is going down as you get farther and farther away from that inner ring of circulation, of vorticity. Okay, so this is just cool to look at. You can find lots of other ones like that too, and lots of smoke ring ones. Though I don't think you can make any smoke rings that are like the ship that Gandalf does in the Hobbit. That one doesn't, there's no vorticity balance in that. All right.
Apparently needs to bring in cigars that he does back in the day.
Oh yeah. Yeah, exactly. You could very, yeah. In a previous era, yes, I was very good at blowing smoke rings. So anyway, not anymore. Okay, so, all right, so we have this relationship between vorticity and the vorticity equation. There's also, we could have integrated that and made, just like we made, momentum of the Ekman layer or total salt content, we could integrate and we could make equations for the evolution of a circulation. And so it would have, and it would have a relative part and it would have a planetary part. And so we could think about how that works. And if we go back and look at our vorticity equation, without watching the movie again, if I managed to make all these terms, if it wasn't baroclinic and there was no friction, and it turns out these two actually, with symmetry, you can cancel them out. You could find something that just said that the circulation would be conserved. So whatever you do to a material surface, whether you bring it in, stretch it tall, pull it out, you would end up having the same circulation. So the vorticity is going up and down, but the circulation inside that material surface is the same. So this is kind of a different way of thinking of the same idea. Unless there was baroclinicity or friction, and then you could produce circulation or produce vorticity with that. So inviscid barotropic fluids, no baroclinicity, no friction, preserve their absolute circulation, both the relative motion and the summation across R bit, the integral of the average normal absolute vorticity within a material surface. Okay, that's kind of complicated. All right. So there is a simpler object to think about than vorticity, especially when we're thinking about motion in the horizontal. It's called potential vorticity. So the complicated part of this stretching and squeezing is that you have to keep track of how tall did the column used to be and now it's gotten shorter, right? So it wasn't moving and then we stretch it and now it is moving. And then when we squash it back, we have to know how far did we have to squash it to get it back to where it started. It's a little bit complicated. Okay? So potential vorticity is basically the idea that you track both the vorticity and the height, and you take their ratio. So as I get taller, I spin faster, but I'm also taller. So if I take the rate of spin, F plus zeta, and I divide it by the height. When this one goes up like that, it spins faster, but this one will go up too. Or if I squash it, I might get more anticyclonic, but I would also get shorter. This one goes down, this one goes down. So this thing doesn't change when we stretch and squash it, but it kind of nicely tells us the ability that if you were to stretch and squash, we could take the same value of Q and figure out how fast it would be spinning at different heights. Does that make sense to everybody? So, potential vorticity, because it doesn't have a stretching and squeezing term, is actually just materially conserved. There is no stretching and tilting term. It's just ddt of this thing equals 0. So it's just like salinity. So once you've labeled all the fluid with its potential vorticity, if it's inviscid, and then it just holds on to that potential vorticity, actually inviscid and there's no baroclinic torque. Then it just holds on to that potential vorticity as it moves around. Which is great, because that tells you like how much spinningness you're going to get as you move through around the fluid. Like, so I start one piece of the fluid spinning, and then I move it somewhere else, and it gets stretched and squashed and whatever. But if I just keep track of the potential vorticity, which I know is conserved following that motion, I get the value that I would ultimately have in different conditions. And this, so look at this equation, pretty simple. That's a simplification of, oh, whoops. That's a simplification of this equation, pretty complicated, which is a simplification of this equation, of the momentum equation, also complicated. So we've gone from really, really complicated equations down to something that looks just like the salinity and temperature equation, which is pretty simple. So if we can get ourselves into a condition where the potential vorticity is the governing dynamics, then we just need to track the potential vorticity, the salinity, and the temperature. And that would be it. That would be all we need to know how the motion works. Okay? And so that whole notion that that's the way that things possibly go drove the way that large-scale oceanography went for a long time. And we're going to try and think about how to think about vorticity in the circulation, but from this equation it's actually going to help us think about how the gyres work. Okay, if we played this game for the reduced gravity case, which we could, we would get a potential vorticity which is just this same one, that it's F plus the vertical vorticity over H of the moving layer. Okay, so we can redo the Taylor-Proudman theorem based on vorticity. We can redo the thermal wind relation based on vorticity. We can redo the Ekman relation based on vorticity, because this one has a dVdz in it, which is a kind of vorticity, right? That's a rotation about this horizontal axis. The Ekman spiral has a dVdz in it. It's a rotation about the vertical axis. The Taylor-Proudman theorem is not an overturning. There is no vorticity in the horizontal. There's just vorticity in the direction of the rotation axis. So I claim that all three of these, we could do it again, and we don't have enough time for me to show you how to do it. But essentially, we can take the vorticity equation and go through canceling out all the terms in it and find out the Taylor-Proudman theorem. It pops right back out. It says that there's no tilting in the direction of the axis of rotation. We can do Ekman, and we find that there's that, which is basically says the curl of the friction force, that is the wind stress essentially, is giving us some shear in the direction of the rotation axis. So that's the Ekman spiral in vorticity language. But the one I really want to talk about is to start talking about the gyres in terms of how their vorticity works. Okay, so the gyres are going around and around. Like the Gulf Stream goes north, and then it comes back. And last time we saw that it follows pressure contours, and those pressure contours are piled up on the west side, but you loop around and around the high pressure at the center. Which component of vorticity is important for the gyre? Which one controls the strength. The vertical component. And will the subtropical gyres have cyclonic or anticyclonic vorticity? Relative vorticity. Sorry, clear. Anticyclonic. They're going around in a clockwise direction in the northern hemisphere, counterclockwise. They're a high pressure system, so they would have anticyclonic vorticity. A low pressure system would have cyclonic vorticity, so the subpolar gyres are going to be spinning like the pole that they are closer to. Okay? So if we look at the map of pressure, we have these circulations. They're going around. These are the high pressure zones, or the anticyclones. The low pressure zones are the cyclones. This is a big honking cyclone that goes all the way around the planet on that side. And we know at depth, most of them cancel out. So we could use that reduced gravity up one layer of motion if we wanted to think about it that way. Okay. So we have this potential vorticity relation that says that the relative part of the vorticity plus the planetary vorticity divided by h following the motion is going to be 0. Okay, so we somehow want to get this idea together with this picture, which is a little bit complicated. And we also have, is the Rossby number of the gyre going to be big or small? Small Rossby. It'll be rapidly rotating. So F will be big compared to zeta. F is big compared to zeta. So looks like we're going to have to be kind of, and then how does F change with latitude? It does, right? Because the closer you get to the pole, the more like 2 omega it is. The closer you get to the equator, it's more like 0. And then you get close to the South Pole, and that's negative 2 omega to 0. So we have a bunch of things to think about here. Okay. So let's look at this PV. So here's our PV, which is the same as this, which in the small Rossby limit is approximately just F over H. So I'm rotating with the planet, and I have some thickness. If this is conserved, then moving to larger F means you could either, if F gets bigger, what has to happen to omega z?
Decrease.
It has to go negative or decrease. So I'd have to start rotating more anticyclonically. That's one choice, but I have another choice. I could also make F bigger if I make H bigger. So I'm rotating with the planet. I move. Which direction gives me larger F? Northward. Yeah, or larger magnitude F if I go in south. So if I go poleward, I could either start rotating anticyclonically, which kind of makes sense. I start rotating the opposite direction of the planet. So I'm conserving my sense of rotation. As I go closer to the pole, I start rotating against the pole, so I'm still rotating at the same rate. I'm like opposing the sense of rotation I would gain from my environment. So my relative motion starts to cancel out the change in this one. That's one way to do it. Or I could have stretched. F could have gone up and H could have gone up too. So I could have just gotten taller. And then I wouldn't have had to start spinning. Okay? If H was deep, now let's not worry about changing latitudes. What if I just squish a parcel? I squish a column of water. If I squish this, I'm making H smaller. What happens to zeta Does F change if I squish zeta sitting still? No. So I would start to rotate anticyclonically. I have to make the numerator smaller. So I could start rotating anticyclonically if I got squished. Or I could have actually moved equatorward. And then I would have had no relative motion. So in order to conserve potential vorticity, I have two choices. I could either, so when I move around, I can either add or remove relative vorticity, or I could increase and decrease my thickness as I'm cruising around. Okay? So does the gyre have a lot of relative vorticity? We just asked this question in different words a second ago. What's the Rossby number of the gyre? Small. So it doesn't have a lot of relative vorticity. So we could just kind of cancel out this response and this response. And now you're starting to see that we have something powerful happening. If my H increases, I'm going to move poleward. If I want to avoid building up relative vorticity. And we don't know why the gyre is avoiding building up relative vorticity, but it is doing it because it doesn't have any, or it doesn't have very much. So if I stretch a fluid column, it's going to start to move toward the pole. If I squash a fluid column, it's going to start moving toward the equator. That's what conservation of PB saying that zeta is negligibly small tells me. Does that make sense? Okay. What motion have we talked about that squashes and stretches interior columns of fluid in the ocean? It's related to the paper you're writing right now. If you are upwelling into the boundary layer, what are you doing below the boundary layer? You're taking the top of that column and pulling it up. You're stretching underneath. So whenever we have Ekman upwelling, we are stretching the interior of the fluid. Whenever we have Ekman downwelling, we are squashing the fluid in the interior. Whenever we have Ekman upwelling, we should expect to move to larger F. Whenever we have Ekman downwelling, we should move equatorward. Okay, so so we can do this with little columns, which this is just showing like toward greater F, whatever. This is just saying the same thing in words. But let's look at our little schematic. Okay, here's our winds in red, our Ekman in purple. Where do I have Ekman downwelling?
20 degrees.
20 degrees, minus 20. So basically, where these arrows are converging, it's going to go together and it's going to downwell. Where they're diverging on this side or this side, upwelling. Okay, converging, squashing. Am I going to move toward the equator or toward the pole? Toward the equator, because I need to slow down my rotation and if I want to stay at the same rotation as the Earth. So everywhere in these convergence zones, I should be going equatorward. Everywhere in the divergent zones, I should be going poleward. So that is the essence of something called the Sverdrup balance, which is a vorticity balance that says when you have a curl in the wind stress, why is the curl in the wind stress important? Exactly. That's the thing that's proportional to upwelling or downwelling. When you have a curl in the wind stress, you will have meridional motion. Motion either toward the pole or away from the pole. And it's in such a sense that if you are squashing the interior fluid columns, you move equatorward. If you are stretching the interior fluid columns, you move poleward. And now I've also drawn the gyres on top. So Sverdrup, Sverdrup, Sverdrup is always going one direction, but the gyre actually loops around like this. How do you think that works? Is Sverdrup conceivably part of the gyre circulation? This part is going in the same direction, the eastern side, the eastern side, the eastern side, the eastern side, the eastern side. And it's also true here, that the eastern side is going in the same direction. The eastern side is going in the same direction. So remember what we said about the gyres. There are big currents close to the shoreline on the western side, and the eastern side is a broad, slow drifting thing. The Sverdrup relation is apparently telling us about the broad, slow drifting thing. And now we can go back to our PV equation and say, all right, I'm sure no one remembers what assumptions I had. How do I say PV is conserved if what? What were the terms I threw away over here? Or terms that I talked about there possibly being on over here? Friction and baroclinicity. But friction is one really important one. So what if, whenever we're away from the coastline, we don't have any appreciable friction? Then the Sverdrup relation and the eastern side of the gyre circulations are totally consistent. Then when we zoom back to go in that fast boundary current to do the loop around, we would it's going to be a fast current. It probably experiences some friction or something like friction in the equations of motion. That might violate the Sverdrup conservation. So we're conserving PV, then we zoom in and we inject a lot of PV using friction. Then we conserve PV, and inject a lot of PV using friction. Conserve PV, and go back and forth like that. Yeah?
How do you know that PV is injected by the friction?
How do I know that it is? I just know that it is. We're going to do it. We will move on to that stage of the next piece. We'll start to think about how the friction comes into this vortex stretching system. And what the easiest way to think about it is now we're going to add another Ekman layer, not an Ekman layer on the top, but one on the bottom that's there because of bottom drag. So that we had a frictional force from the winds up here, but if we're moving relative to the bottom, we should have a frictional force on the bottom. And we'll get vortex stretching and squeezing on both sides, and then we'll think about how that all fits to give us this story. That's going to be the Stommel model of the gyres. Yeah.
One more question. Is the reason that the gyres are closed because of the Coriolis force? Take it to the right?
No, the Sverdrup relation is actually totally happy with the Coriolis force. It's already in geostrophic balance. So it doesn't need to swerve to the right. It's happy going in the straight line. Or, that's not quite true. It's happy going north-south. The east-west component of the Sverdrup balance is not constrained by vorticity. Okay, let me see if I had any other things I wanted to say that we're not going to say next time. Okay, we're going to pick back up around here next time, where we're going to start to say, we're going to talk about vortex stretching and think about the meridional transport that we're getting because of the Ekman transport stretching and squeezing us and which way we're going to go. We're going to come up with an equation that gives us the rate at which we move toward or away from the equator based on the amount of Ekman stretching and squeezing. And then we're going to start to think about adding a bottom Ekman layer on, and we put those two together, and we're going to figure out whether gyres go this way with the big currents in the west or go this way with the big currents in the east. And that's going to be only one way to do it, when we think about whether friction could be on this side or friction could be on that side. Okay? Are there other questions? There are other questions about the paper too, while we're standing here.
Yeah, I have a question about calculating action transport. So when we are calculating it over several grid blocks, shall we just average it? Or?
You can average it or you could sum it up. So the units of Ekman of tau over rho f are velocity squared per. So it's kind of mass transport per unit length. So we talked about this last time. So it's the integral of velocity dz from the bottom of the Ekman layer to the surface is tau over rho f. And I've forgotten which way it has a z hat. I can do it this way. So this is velocity times depth. So it's not volume transport. It's meters squared per second. I need to integrate this way in the horizontal to get the meters cubed per second volume transport into and out of the box. So if I put one box, another box, and I have, say, wind stress going this way, then I can calculate the flow per unit length, or I can integrate it all along this boundary, which would be dx. Sorry, I'm gonna put this sideways, but and this north is that way. East is that way. The way I wrote it. Sorry.
What if there's like two columns of boxes?
Like this?
Yeah.
Okay. Then, now we have conservation, so we know that whatever's coming out outside is going into this side. So you might think about it through a curtain here or through a curtain there, but you don't add them together. You would just take the outer one.
Okay.
And so if you were thinking about coming into this volume, you might calculate the flow through this wall, the flow through this wall, the flow through this wall, maybe this is the coastline. You don't need these these don't affect the base and the budget of that whole set of boxes.
Oh.
Because whatever's coming out of this box is going into this one, so it doesn't affect the budget. Does that make sense to everybody? And then you'd have the upwelling at each of these points, and you can add those up. And that would be like an area integral of all of those little upwelling values. And just like in the homework, you want to use the units to guide you to figure out whether you need to multiply by 1 dx, 1 grid cell width, or dx and dy in order to get the vertical one. You want to check the units and guide yourself toward cubic meters per second as a volume transport into and out of, or cubic meters per second times the density, which is kilograms per meters cubed, so kilograms per second, or cubic meters per second times the density times salinity, which is the mass of salt per unit time, or meters cubed per second times the density times Cp, so the specific heat capacity times the temperature, which gives you watts arriving, or joules per second arriving in the box. Does that make sense? So use the units to guide how many extra factors you need to multiply by to get those transports in and out of the box. Does that make sense? Yeah.
So the curl of tau by f, is that already the Ekman transport calculated for us?
It is the curl of tau by f, and it's not the Ekman transport. It's just del cross tau over f. And I think there's a row that you need to add.
Okay.
So I think you need to divide by rho to
Okay,
get
so
to
it's just
W.
that rho and then it is the Ekman transport?
That's the Ekman vertical part of the Ekman.
Oh, okay. Just okay.
Yeah.
That makes sense.
Does that make sense?
Yeah, so it isn't any of the horizontal.
It's not the horizontal ones. It's
Okay.
only a scalar, so it's just one of the three components. But the curl one is the one that's the vertical one. And the curl of tau, you could also do the curl of tau with 1 over rho f outside and see if it's any different. If you're not near the equator, these tend to be pretty similar. But this one is the one that really gives you the Ekman upwelling. This one is an approximation to it. And we'll see when we get to the Sverdrup business that things start to get really interesting because there's a tau and there's an F inside, there's an F outside. You can add them together and do kind of a fancy little bit of dancing. So we actually want both. It'll turn out that Sverdrup is more easily understood from this one, whereas Ekman is more easily understood from this one, which isn't obvious at all. But well, there's a reason why I gave you both of them.